if someone wants to screen share, they can.
Yeah, maybe.
Cool. I can screen share. I'll screen share the document.
Okay.
Oh, there's a transcript? Oh, okay.
Pardon?
No, I just noticed there's a transcript. I don't know if one should put it all or it's quite distracting.
Where is that?
I think you can set that yourself. I think so. Okay. Cool. Do you guys want to introduce yourselves?
Well, I guess we can go from the top of the group members list.
Okay.
Well, Daniel isn't here.
No. Gareth?
Cool. Yeah, I don't really know what to say. I'm Gareth. I'm studying computer science.
I'm Joseph. I study physics.
I'm Matt, and I study comp sci as well.
I'm Audrey, and I'm done studying, but I studied human life sciences, so BSc.
I'm Rizan, and I study biomathematics.
Cool.
Cool. Yeah. So maybe we can just start off by explaining how we found this project, or like what was the process behind us working together, and then just take it chronologically. You guys fine with that?
Yeah. I must say it was quite hard to get into the groove to actually figure out exactly how we should approach the assignment, how we should still work as a group but individually. I think that took a long time for us to figure out. It's like it's individual, but it's also a group, and everything has to make sense. And I think like Matt, if you want to say something about like starting with a different topic.
Oh yeah, I think in the beginning we had a few people that had done operations research, and it seemed that everyone was like, "Oh, cool! This seems like a very cool idea." And I think in the beginning we weren't 100% sure what we were meant to be doing, and I know not many of us could make the meetings. Like Mildred, you teach until late. I had hockey practices during lecture times. And so I know some of us couldn't make the meeting, so we weren't really exactly sure how we'd go about it. So we did end up choosing a topic that was a little bit out of reach for us at the time. So then we kind of set ourselves back already by choosing graph theory, and also then changing. I think it was about 2 weeks later.
A week or two, I think.
Yeah, and then. Yeah, then after that, I think once we got set theory, even once we had the topic, it was fairly difficult to figure out what we should be doing. And then I know, like for myself, I chose like subsets. But then when I was trying to find different things in subsets and then other definitions that maybe other group members were using or maybe not using, and then if those followed onto my section, and then I found it very difficult to, I guess, find a starting point and to be confident in my starting point that I was going. But how was your guys' view on your starting point of the project?
Joseph?
Yeah, for me, it was also quite difficult to start. Also because I wasn't. I feel I got more comfortable with the proof structures in this assignment than I previously was, because I started off doing them wrong, and then and then later they got better. So
Yeah, it was actually quite interesting seeing your work growing. Like
Yeah,
you started off and you always left notes like still needs work, and then a week later you see it like tripled in size. So for me, it was actually the hardest part to start, because I knew what was expected of us was to start off with axioms and definitions. And I think to find those axioms and definitions was the hardest, because we did some of them in class, and also some of the definitions we didn't really write out as precisely as I think Prof would have wanted it to be. So I had to kind of also go back to the basics, like what does for all and there exists exactly mean, and like, you know,
Yeah.
kind of just recap all the basic definitions and learn how to read sentences again, because it's like we kind of veered away from that topic of proof structures and logical statements throughout the year, and then kind of came back to it again. So I think all of us kind of
Yeah.
had to go and relearn the first seminar's work. And so
Yeah,
for me, I wanted to get the axioms, and I thought, well, I'm sure they already are somewhere. And I found the ZFC axioms online, and like, and I noticed that some of the axioms that we named as axioms in class were different from those. Like the empty set axiom, we made an axiom in class, but on the ZFC axiom list, it isn't actually an axiom. So I was a bit confused as to which ones do we choose, and do we accept them as true? And I think I'll speak a bit about that later, because I kind of struggled with that. But I think once we found a few definitions to work with, we were able to construct some proofs, and yeah.
Yeah. I think for me, I started looking for theorems first, and then from the theorems, I tried to to see, okay, but where do I need definitions and axioms? Like how do I formulate these things? This is confusing a little bit, but yeah, I started off with, I remember when we had the first meeting of like, okay, let's switch to set theory. Or just let's switch to something else. My first thought was, what did I enjoy most this whole year? Not really realizing, we actually did a lot this year. And if you like start somewhere, it like goes a little bit, you can go off on a tangent quite quickly. So also started off looking at like relations and composite functions and stuff. And when I like did a little bit of research on that, I'm like, okay, nope, let's go try something a little bit different. So then I thought, okay, well, associativity, distributivity, and commutativity is something that we've been using since like grade 8. Actually, even like earlier, but like I remember this year I taught my kids that in grade 8. So yeah, I thought it would be quite interesting to try and combine union and intersection of sets with commutativity, associativity, and distributivity. So first try to look up proofs and thought of like, okay, but logically in the sense of just talking about it, what do we have? So my first draft was terrible, quite ashamed of it, but it's fine. Yes, so only after like finished at least just jotting something down so that you like have a place to start. Only after that and building a proof, like an actual proof on that with Ruzan and with Prof's help, only then I realized there's so much more, and then the process actually started for me. So yeah, it's been a journey, but it's been interesting. It's very interesting.
So, go.
Okay, yeah. For me, I think I went right off the tracks to begin with. I think I misunderstood what the assignment was sort of supposed to be about. So I sort of like right at the beginning sort of started to try and think of interesting new ideas or interesting ideas that we hadn't heard of before or something like that. So yeah, I sort of started right in the wrong place. So I think we included a little bit at the end. And I remember in like if you look at our very first sort of draft version, like yeah, my idea was to sort of look at how we could represent numbers as sets, which was an idea we were introduced to. But then sort of to go further with that and explore what possible sort of mathematical operations you could perform with those sets and how that would relate to numbers, sort of coming up with an idea of like what would addition, subtraction, multiplication, and division look like using numbers as sets. Yeah, but I was quite far off what the rest of the group was doing, so I was kind of pointing in the wrong direction and heading fast.
Just an interesting note, like I think you probably looked so far into the future in a sense, like you wanted to get to the effects of, or the, what do you call that, what set theory leads to, and which is cool because like all of mathematics is technically rooted in set theory, and you kind of just wanted to get there, which is still okay. But I think I think the aim in this project was for us to re-examine where it came from, and instead of looking into the future, kind of re-examining the building blocks and then building up this theory from scratch. Which is quite odd to do if you grew up kind of with the idea of set theory. I mean, in school we learned about sets, although that's technically naive set theory, not really the type that we learn about in university. But it's just interesting to kind of take something we already know and trying to prove it from the most basic assumptions. It's actually more complex than you think it is. There's way more assumptions involved than just axioms. And I think that's maybe something we all struggled with, is the idea of how do you use logic in proving something? Because from what I gathered, a theory is a set of axioms, which are the assumptions you start with, combined with the definitions, and then you have to derive theorems out of that. But then I realized, as I struggled with one of the concepts behind, one of the axioms was that we actually use more than just the axioms, and that's obviously logic. Like, how much can we assume before we even write down those axioms? That was just something I struggled with, and I think, Mulji, you also used the distributivity and associativity and commutativity of the logical and or operations that we really kind of assumed. And you kind of took those as your axioms because you identified that those were your assumptions. But I think that's where we sometimes went wrong, is like distinguishing the logical assumptions, which we don't really have to write down, and that, I don't know, something I just realized.
Good. Mildred and Razan, would you guys like to kind of introduce set theory?
I think we've all said a lot already. I think like the gist of it is set theory is more than just math. Set theory is more than just something precise or something structured, or it can be applied to anything, not just mathematics, obviously in the broader of mathematics, but also in real life. We can think of things as elements, we can think of things as sets. If we think of, let's say, for example, specific elements that are in something else, that the elements is elements. But
I think what you're trying to say is that elements can also be sets.
Yes.
So a set can be
and a set is contained out of elements, and the universe of sets is like a collection of sets. So
and I had something I wanted to say, but I think it's also interesting for me to read up on the history of set theory. Maybe that's what made me so hesitant to want to kind of just identify the axioms by my own like intuition, is because I know there's a lot of history behind set theory. For example, there was naive set theory, and then it was proven that, with Russell's paradox, that you can't have a set of sets that do not have themselves as element or as members. I don't know, that whole paradox, like, basically, I don't know, it's a very it's a fascinating topic for me. So I was a bit hesitant to identify axioms for myself, which is why I went on Google and tried finding these axioms and then working with them. And I think that might have been a mistake, because I think they are quite complex in some cases. And it's hard to use them if you don't understand them 100%. It's just really interesting reading up on the history of set theory for me. But anyways, I think we should maybe move on to the actual proofs.
Could I just quickly say something? So just a quick thought on what sets are and sort of thing. Obviously, doing computer science, I like to think of computer sciencey sort of ways of describing things. And how I think of it is sort of, you can think of any application as being built up of different components. When you're coding, you have different objects, different classes, and sort of you have things that expand from more basic principles. And so to me, I see sets as sort of, if this was programming, sets are like the ones and zeros. It's the very, very basics of what a whole pile of really interesting other things build up on top of. So yeah, I don't know if that's really a good analogy, but yeah, it's like sort of the basics of what you can come to agree on and build something much more complex out of. Yeah.
Isn't Boolean logic used in computer science quite a lot?
Yeah.
I mean, Boolean logic is also kind of like the set of truth and falsities.
Yeah, it's really interesting. I mean, this whole topic really interests me.
Yeah.
I'm just evidently not that great at proving it.
Okay, guys, we're coming up on 42 minutes.
Yo.
Oh, mine says 30 minutes.
Although I think
Oh,
that's
but
just
I
from
think
the start of the meeting.
yeah, the timer is from the start that we opened the meeting.
Yeah.
Oh, okay.
I don't think we have a recording timer.
Okay. So we should we move on?
Yeah. Would you like to talk about in any individual definitions or axioms, or would you guys
Actually,
like
can you go to the first axiom?
Yes.
I had a bit of a so I had an interesting experience. I think I wasted a lot of time, although I wouldn't say I wasted it because I kind of did learn a lot out of it. But I doubted whether one should make that one implication an equivalence in the extensionality axiom. And there's a reason why I doubted it, because as I said, I consulted the internet in finding all the axioms, and on most of the sources I found, they only had the one-sided implication. And I was wondering, but why can't we just make it an equivalence? And at first I did like kind of change it, but then I started rethinking on it again, and I thought that maybe because I know these people have put a lot of thought in it, there must be a reason why it only goes into the one direction. Like for x, if x is an element of x is equivalent to x is an element of y, then x is equal to y. That then can be equivalence as well. And I kind of got into like a little bit of I confused myself in thinking about the concept of equality, because we're making this axiom for equality, yet we already kind of have an idea, like a presupposed idea of what equality is like. And I was thinking, like, should we first define equality before, or because we're kind of defining it by using the axiom. And luckily I dwelled on it quite a bit, and I even wanted to like see if I can come to contradiction if we do take it as an equality. And I did attempted a proof on wanting to show that it can lead to like that you can both prove that a set is equal to that all members are part of the set that are equal, and that they are not, using the empty set, because the empty set is defined as x is an element of the empty set implies false. And I thought if false can imply anything, then surely one should be able to prove that that the empty set is both equal to itself and not. I know it sounds quite bizarre, but I kind of dwelt on it quite a bit. And then luckily I consulted Prof for it, and he was a bit like, why? It's of course it can go in both directions. And then I realized that I was actually missing some of the logical tools, because he showed me why both directions should logically hold, because substitution is actually one of the logical rules. And so he said that if there's an X, like an object X, and there's a property for X, then one can conclude the same property for Y if X is equal to Y. And so I kind of missed that, and I was wondering if one can assume like substitution before you actually write out the axiom. And yeah, it turned out I was just missing some logical tools there. So that was an interesting experience. But yeah, I'm glad I didn't dwell on it too much, and then got to, because I remember someone also wanted to use it in the other direction, and they made a note on the document, because I originally put it in the one direction, and I think you also found the same like problem, that if you don't have that as an equivalence, you can't conclude anything from X is equal to Y. Except I think you can still use substitution, which means that backwards direction should have just been part of the axiom. So yeah, that was just an interesting experience I had. Anyways, I think we can go on. Yeah. Oh, I can just mention something about this. I know we did do this in class, but I think my method of like recapping or like remembering proof structures were just redoing things that I remembered from class. So I remember just like thinking about, okay, what is something that I can do by myself, and then just check if my logic makes sense, to make sure that my fundamental like tools are still in working condition before moving on to like larger proofs. So I first did like very short proofs on the reflexivity and transitivity of like the subset and equality, and then I felt like I was comfortable enough and remembered enough to like start attempting longer proofs. But Matt, you also kind of like did this one by yourself, and you kind of did get to the same.
Yes,
like,
yeah. I think because I wanted to try. I was going through when I was still in the beginning of the project. I was going through some of the things, some of like the old videos, or I guess the old videos that are now. They're old now. I was going through them, and then I saw something that was similar, which was it wasn't the structure that had been done, but it was the idea of the proof of the set X is equal to X. And so I used that, and going through this, I then went and got a structure, like kind of one of the old structure videos from the beginning of the year, and then used that to prove that X is equal to X. And then in doing so, I had the correct structure, but I did this quite a bit before I did my later proofs, and that is also maybe why I forgot the actual structure, because I did it at the same time, and not actually learning it while I was doing it. I kind of just went through the process of doing it.
Yeah.
But yeah.
I think for all of us, it took quite a while to just remember, okay, what is an assumption? What is a conclusion? Like, what do you have to introduce to assume something? I think one of you also said, like, if you have, Matt, I think you said, if you have a French person, you first need to have a person, and then classify the person as French, before you can make any conclusions. So just actually have gone through that process of like, you can't just say A union B. You actually have to say there is an A, there is an B, and something is happening to them. So it's quite interesting to actually just like re-examine everything.
Yeah, that's why I dwelled so much on the assumptions part, because it's actually quite fascinating. Because it really is that if you start with the wrong assumptions, you can prove anything, and you can prove absurdities. And I think I really dwelt again, like I already did dwell on them on the first semester, but I re-dwelt on them, like the concept of the false implies anything, and that you need a starting assumption in order to conclude anything.
Yeah,
I
kind of just wish we did more of this throughout the year, not just in the first and the last seminar. But
I agree.
Okay, Gareth.
It's quite funny. You're mentioning this now, and it's sort of back to programming. I've been trying to help my girlfriend with learning C. She's doing civil engineering, but it is quite funny. Sort of, you see the process that people who aren't used to programming going through, trying to get a sort of chunk of code to work. And it's like, well, before you can use a variable, you've got to define the variable. And in some cases, you have to give it some value to start off with. Otherwise, the computer doesn't know what you're talking about. So I don't know. I find it interesting that, I mean, proofs are very much like computer programs. You've got to go step by step. But there's a big difference between a mathematical proof and a computer program. And I think my brain's much more wired towards the computer program than a mathematical proof.
Yeah,
I think the thing behind in computer programming is there's already kind of programming within the programming. Like every function you use has already been written. So there's already like someone already had to think about a certain function, write it out, and then you can just recall that function. And I think maybe as a computer scientist, you might, not think about deconstructing each function you use into the smaller steps.
Well, there's some really interesting stuff when you get into assembly. You're actually giving instructions to the processor. But yeah, that's a whole nother ball game.
Yeah, I think I can resonate with that a lot because I learned how to program when I was about 13. So all those like simple basic things like I do tutoring as well, and then like a truth table, for example, and using and or and that, it seems to come naturally. But then when someone asks me to explain to them in the program and why why this order of the or and or statements work, I can tell them why, but if they don't understand, I kind of don't really know how to explain exactly why it works, but like in my mind, I know exactly how it has to be for it to work. But I think that's also one thing that's very nice about university is, like Rosanna was saying, how the functions are there and we don't think about deconstructing the functions. I found a lot of, I guess, self-taught developers, like they say they don't actually learn how to deconstruct functions, whereas in university we are made to make our own functions, and chances are we're not allowed to use a tool that's already out there. But there's no documentation of exactly how that tool works that is out there. So you have to take this project and engage it with it by yourself to be able to solve the problem. But there are tools for after that. But yes, Mondi?
I experienced this a lot with this whole module. Is like the internet has information on definitions or basic concepts or whatever, but it doesn't go in depth of like how to actually do it.
The proof structure. But that's why Prof said we can consult the internet, because we might find identities to prove, but it's not going to give us the proof on a plate. Like you still need it. And I think that's what I kind of tried using to our advantage, is using the internet as ideas of what to prove. And because if you want to prove a theorem but it's unprovable, you're going to have some problems there, you're going to struggle. So I was like, let's just find some identities that we know also intuitively to be true and then prove them, which is also kind of selective in a way, because then which I felt like then you don't get to really struggle enough, but maybe we needed something not to struggle with in order to know when we're struggling, in a sense.
Especially since I think we saw now, just like Rosanne, like the commutativity proofs of intersection and union, we all thought, hey, commutativity, yay, cool, that. So easy. The moment you start proving it, it's like, oh my word, there's so much in it. So there's everything's just so much more jam-packed. So it's actually good to start somewhere that you think is simple, and go from there.
Hey, Gareth, do you want to speak about that previous proof?
Yeah.
Yeah, I mean, there's it's not a heck of a lot to say there. It is a fairly simple one. I was just sort of wanting to test the waters with Sophia, and sort of try it out. Obviously, with Sophia being made in Python, it sort of clicked my interest because obviously I enjoy computer programming and stuff. So yeah, I just wanted to sort of test the waters with Sophia there, play around with it a little bit and see how it worked. Yeah.
Okay, yeah, I'd actually just like to talk about the references, which was the thing he had the biggest problem with. I think, well, I added these references at the end very hastily, and well, I don't think that was so smart because, of course, if I get that wrong, then it does suggest that I don't understand the bracket structure that well. Um, but because I added them so quickly, I think I do understand the proofs better than what this suggests. Uh, but I'd maybe just like to go through a few of my errors. Like for instance, everywhere where there's an assumption, I don't think it's necessary to say that it is an assumption because it's quite clear. In line 7, I mentioned that I got that line from line 2 and line 6, but line 6, I thought I should add that because I assumed it, and I thought I needed that assumption for that statement, but it turns out it's not necessary. And then the other problem was with line 9. I should have referenced line 6 as well because line 8, the implication symbol works sort of like an if statement in computer science, and I can't have the right side of the implication statement without the left side, so I should mention the left side. And then other than that, line 17, I should have mentioned line 14, again because of the implication symbol. And yeah, just in line 23, I should have mentioned line 20. I think again because of the implication symbol. And yeah, I think that's it. Yeah, and again, all my proofs pretty much have similar problems with the referencing, so I think we can skip over there.
I think maybe I'm keen to maybe discuss how we actually formulated this proof.
Oh, okay.
I remember when Joseph was like when Razan said that when he was building up his proofs. I don't know if we started the recording then or if we were just having a chat before we started. But then how Razan was saying like Joseph was building up his proofs and he wasn't sure about one of the proofs, and I had a morning off, and I decided, okay, cool, I'm gonna engage with this proof and see what I can produce from working on this proof, and it ended up I seem to have got the idea correct and the way things move correct, but not the structure. So I think I managed to prove it, but not in the correct way that we needed to. And then I shared this with Joseph, and then Joseph and I were basically talking about it. And then I asked Razan if she could help out with this proof, and then she actually ended up kind of explaining the bracket structure by using this proof as an example. And then I found it very interesting, and I think I learned more about the proof structure, but I still seem to have not got it fully correct. But I understood a lot more about what happens in the structure as opposed to from knowing nothing.
Yeah, I just want to add there. So, because that was on the Zoom session that we had, I kind of just used this as an example of how to build up your structure before going to the meat of the problem. Because I think most of us normally, when we want to prove something, we first think of the logical, like meat, which would be like the inside of those brackets, like after you've assumed stuff. And then you kind of have to work backwards and find out what your assumptions should have been. But I wanted to show that if you start with your axioms, if you first identify which axioms you need to prove something just by looking at your identity, and then looking at the theorem you want to prove, and then working backwards, almost as a sense, like first getting your structure ready and then working inwards. And then I also wanted to accentuate the fact that if you want to access what's inside the axioms, then you need your assumptions, because, for example, for all x and a certain statement or property of x, you first need to have an x before you can access what's inside that statement. And that's why I always referenced my, before I, let's say, use what's inside an axiom or a definition, I first state the x, and then when I reference what's inside the axiom, like under the x, then I would reference the x and the axiom that has the for all quantifier. But yeah, so that was just one of the things that I wanted to accentuate. Yeah, so we just basically, we all worked on the outline together, and then I kind of left the meat part for you, and then, yeah, so how we all kind of
Collaborated on this.
collaborated.
Okay, Joseph, I don't know if you want to talk about this one as well, or
No, it's all pretty much similar problems to. It's mostly problems with the referencing, so I think I'm fine.
But I do think, Joseph, like, yeah, I definitely saw your understanding increasing as time went by, because you also did very short proofs, and then by the end, like, your proof structures really did improve a lot.
Yeah. Yeah, I just didn't know I should be so meticulous.
Cool. Should I go down to Mildred's first proof? And would you like to just kind of discuss how you came about it, Mildred?
Rosanne's ones are first, if she wants to go first.
Rosanne, would you like to discuss another?
Yeah, I kind of just said more or less what my, like, method was behind it. Like, I would first obviously identify a theorem, and then I think a lot of thought went into the theorem itself, like how to phrase it correctly, and then to prove it, you kind of have to work with your theorem. Like, if you want to prove something for all x, you have to first assume an x. And same with for any two sets A and B, you first need to assume two sets A and B. Maybe where I might have went a bit off was where's the can you maybe go to the distributivity? One of the distributivity groups. Yeah, maybe the next one. Oh yes, there. So in a lot of these distributivity proofs that Audrey and I worked together with, I kind of actually added the top part where I would state the set and then kind of substitute it into the axiom, more to get the axiom in the right form to reference it later. I do think that it was kind of unnecessary to state those sets, but in a sense, it kind of does follow from the fact that a set exists. So I thought that it's kind of not really necessary to state, but I didn't think in the moment that it was incorrect to state, let's say, like, let's state A union B as a set, because it kind of follows from the existence of a set. So I should have probably maybe made a note there and said, like, that this follows from the fact that a set exists. And then you conclude that, yeah, anyways. But yeah, so I found the or statements sometimes quite challenging. And I really actually had to kind of play around there. And I really had to reflect on the logical tools of the or statements. And I think I got to a point where I felt like I really understood it better. So I think that was like the bigger challenges of these. But I do feel like overall my proofs were a bit too repetitive, like dealing with subsets, union, and intersection, and equality the whole time. I should have actually maybe rather left some of them and just moved on to something like power sets, or moving on like the pairing axiom and using like a better combination of more axioms. But I kind of like, I just wanted to make sure my understanding is solid before I move on to those things. And then I kind of didn't really end up having enough time to explore them as well. So, yeah.
Yeah, I think so. My proof's problems are very similar than Joseph's. My referencing was flawed. I know for yeah, if I look back at it now and I look at the comments, I'm like, obviously. But yeah, I think in the moment I just didn't think about it too much. And also, like Joseph said, I did it like he did it quite last minute. Same. I started running out of time, so I felt like, okay, let's just get this done. I really just want to get this done as soon as possible.
I think the referencing is kind of like,
it's
it
very
actually
important.
helps you in a sense. You want to go through your stuff and be like, where did I get that? That's way up there. And then reference kind of, so it kind of helps doing it as you do it, but also like if you've added something afterwards and you have to redo all of the referencing. I had to redo some of my referencing quite a few times, which was a bit, but also I think I did spend a lot of time with the referencing, like rechecking my referencing afterwards.
Yeah, I think that's where I slacked. Like I didn't recheck. Above, like I'd read the things a lot. I didn't check the referencing. But yeah, it makes sense now. I think the same with like as Rizwan said, or was a lot more difficult than intersection. It really took a while for me. Like I remember like Rizwan and I, we had like meetings in the evenings, like very late. And we tried to like talk through the things, and I'm like, huh?
I think I only actually started understanding how the like logical, how you can create something from an or statement after like explaining it to you.
But yeah, that's the moment like you explained it to me, and like if you have an A, like thinking about A union B as a set, like let's I remember you said like think about it as alpha, and then or X is an element of A, think about that as alpha, and X is an element of B, think of that as beta. And if you have alpha or beta, then from there, if you have alpha, you can conclude something completely different. If you have beta, you can conclude something completely different, and then that may be the same in a way.
Well, you have to. They both have to lead to the same. Let's say the delta.
Yes.
If alpha implies delta and beta implies delta, then only you can conclude delta. Because I think a lot of thought has to go into what does it actually mean to say either or, because either both of them can be true, or both of them can be false, or one can be true and the other false. And that's why, and that was another thing we struggled with, was if one of them is false, do we have to first prove that before concluding the other one? And it turns out yes, like it has to be fact that one of them is false before you can conclude the other one of them. Anyways, but it's a fun thing to work through.
It was fun.
And I think that's also why I stuck to these, like the more basic ones, to make sure I understand the fundamental logical tools before moving on to more complex things.
Yeah. But it definitely helped, like as you said, to just start with the outlines. Start with like what you want to conclude, what are you starting with. I know that those theorems in set notation, like what do you want to assume and what do you want to conclude, that helped a lot. Like just to actually then start with your end, then work your way up, then go back to the top.
In a sense, especially with intersection and union and the combination, like the distributivity ones, you can confuse yourself quite a lot because you need to identify what is the actual set I'm using, what is the A and B if we apply to the axiom for any A and B, because that A and B can be A intersection B, and so you have to like kind of work your way up and to see what you have to prove in the end from the definitions. Working up.
Cool.
I enjoyed these a lot.
Yeah, it was actually quite fun.
It was really fun.
Would you like to talk about any other proofs in particular? Moldy?
Oh, it's breaking up a bit.
Yeah, I thought everyone froze.
Oh, I see my computer's almost dead. Oops.
I think Moldy froze.
Yeah, multi froze. Yeah, I think we can maybe move on. So actually, I had so many ideas of things that I still wanted to prove. Like I wanted to prove that there doesn't exist a universal set that contains all other sets, and make use of the Russell's paradox thing. And I wanted to actually like see if one can conclude the existence of the empty set from the axioms if you didn't have the empty set as an axiom. But then in the end, we just ended up using the empty set as an axiom. But yeah, there was a lot of ideas of what I still wanted to prove, and then didn't get to. But yeah.
Okay, cool. I guess I'll start off from
Mildred
this
is
one.
completely frozen.
Yeah, I know. So I guess when Gareth and I worked on this together, we had not yet actually done bracket notation. And I remember us, I think I was like, we were on Discord and I was sharing my screen and using like the blackboard and drawing, like just kind of drawing on it and like coming up with ideas. And I think I think we solved the meaty part, but then the flaws in my bracket notation, because I ended up trying to do the bracket notation like last minute, and with not understanding it correctly, it led to a downfall where my bracket notation was just completely wrong. But yeah, so I guess that's kind of what I have to say about these the couple of proofs that I actually did and worked on in this section.
I think just sort of to add to that, yeah, I mean, going through this with you, I think I could sort of follow the proof and it made sense to me, but obviously I don't know. I'm not going to beat around the bush and pretend that I'm like a pro at these proofs, because I'm definitely not. So obviously I couldn't really see where we were going wrong, but yeah.
Yeah, I think it's the same for this as well.
And I think that's the amazing thing about this project is being pointed out where you don't understand something. It's actually very necessary, even though we don't always like being like shown where we went wrong. It's actually very, I mean, that's the only way we actually learn in the end is by not doing it correctly and from someone showing you where we went wrong.
But it's not even just showing you where you went wrong, it's the struggle you had to get where you are, and then being shown like where you went wrong, and then realizing if you just like you went through that struggle, and it's gonna make you not forget that small thing that would have made it correct.
And I think that's what helped me in proof structures is the fact that I really, I know that sounds funny, but I put effort into struggling in the first seminar. Like I was still quite like ready for this module, and like I would sit for quite a while, like struggling with some of the ideas and like trying to prove stuff, and then just that confusion in the end, and then also getting feedback from prof and like listening to lectures and identifying where my problems are and trying to listen to finding like solutions to the problems that I struggled with in that time helped me now, because even though I had to revisit those ideas, it came quicker after struggling. And I think that's what this module taught me, was like struggling is the best way to actually learning something. And also communication with someone that knows better or knows something better than you do. Like Prof also said, like mathematics, you won't be able to really learn mathematics if you don't have a conversation with a real mathematician, because sometimes we have these like we fool ourselves into believing something that in a moment makes sense to us, and then it's oftentimes really hard to unlearn what you've taught yourself, the flawed logic that you're working with. And it's really important that someone points those out to you, so that you kind of get that, like, introspection and like relearn things in a better way.
I think
So it's really a process of learning.
I think like you said, struggling in the first seminar. I think I really struggled in the first seminar, and then after the assignment, and then I wanted to like kind of I got 0 for it. So then I wanted to try like do better, but then the professor said no, he's not going to like accept it. And then I also saw that we weren't going to be using bracket notation and with Dr. Gray or Dr. Hoefnagel. So I was like, okay, cool. I just forgot about it, I guess. And then came this seminar, and it's like, okay, cool. Now I do bracket notation, and from not actually understanding it from the beginning, I basically had to try learn it completely in the last couple of weeks. So I think
And
that
it's
was
not something you can just kind of learn overnight. It's something that really comes with struggling. So yeah, I think definitely.
Yeah, I think I was in the same boat there.
Yeah.
Razan, are there any other proofs that you would like to speak about specifically?
Well, not really off the top of my head. Let me see. I think I've kind of mentioned like overall, what I don't think I need to really go through it in depth because my proofs are pretty like self-explanatory with the referencing. But do you guys want me to go through one of them?
Well, I don't know. I think maybe can I just go through this one? I think for this proof, I put it into bracket notation in the last minute, or try to. And the same process I, like everyone else did, were like, oh, we need reasons or references, and then I also put those in last minute. So I assume they're all wrong, and I understand why they are wrong. I understand why the bracket notation here is completely incorrect, and I also understand why where I messed up and where I can improve.
I think something to note if you ever do proof structures again, like the referencing is kind of like a reflection of the logical reasons, like those logical tools that Croft taught us throughout the seminar, like implication. You can only conclude something from an implication if you have so if you have A implies B, then you need A in order A and that implication to conclude B. So in a sense, in most cases, you need more than just one statement to deduce something from. But sometimes, that's just worth mentioning. But I really find the proof structures fascinating in the sense that it kind of guides you in not making mistakes if you understand it. Like sometimes you won't know. It's almost like you want to convince yourself that something is true, and you use the referencing to convince yourself that each statement is valid. Like each statement has a reason for being there, and I think that's where logic plays a role in this whole. I mean, this is basically deduction, like using one statement and deducing something from that should be true. And that's what's really cool about proof structures for me, is the fact that you have these logical tools that you have to understand, but if you apply them in the right way, you almost can't go wrong.
It's almost like it writes itself later because you extract information from previous lines, and
And the way I see the proof structures are that like almost like a pool of arguments, and like your axioms are your starting assumptions and elements in your pool, and then once you start deducing stuff from them, and you have to obviously have these in between assumptions to access what's inside your axioms. But then once you've broken open those axioms and you know what you want to prove, you kind of have this pool of like statements that you can use and choose out of. Like I don't think there's a strict order in which you have to state things. Like, for example, I could have stated things in a totally other order, but because the referencing in brackets is there, you can still get to the same conclusions by saying, okay, I got that one from there, and then this one from here. But it helps having them in a logical order for yourself more than for the child.
Yeah.
Guys, I just want to say maybe like one or two things about this proof that I did. I think I was reaching a bit too high. I don't think I have enough tools to prove this. But I even went and I in one of the tutorials, and not in the bracket notation way, but in kind of like in words and explaining why this is true and having reasoning in, I guess, my own proof structure. It seemed to, and then Inca helped change it slightly, and in doing so, I understood a couple of things, like in line 9, for example, saying S is equal to T minus X, which implies that T is equal to S plus the element X, which means it's one more, for example, and then using that to then like deduce different properties. I found that interesting, but I also like this. I proved it in my like own way and in words and things like that, with reasonings, but then trying to turn it into a bracket proof, I find I just did it completely incorrectly. But yeah, so that was an experience.
Yeah, I think it helped me to start off with very basic things and then working myself up. And I didn't actually end up doing more more complex things, or like I know I could have gone into more depth, like using power sets and this. But I think maybe the problem here was that we didn't have definitions and axioms yet for the power set, so you weren't able to use them at that stage for this proof. Do you guys maybe want to end off with like maybe something that you've learned out of the project, out of the whole process?
Cool. I'll go first.
Some realizations about life.
I think I think I had a couple times where I felt like I was so unsure, that it was almost like it gave me anxiety that I felt so unsure. And I guess after, like, I don't know, it was, I think, a bit stressful for me because I felt like I didn't know what I was doing, and I tried to put something together that looked similar to maybe someone else's, but I didn't actually. I felt so scared of not knowing, of finding out how much I don't know, than actually going to learn what I don't know. But then, I guess after reflecting on the feedback from the project, it made me also realize that, it kind of made me realize, like, it's not simple, but it's logical. And I went and reviewed a video and then re-looked at one of my proofs that I did, and I completely like want to shoot myself in the foot. Well, I did shoot myself in the foot, because if I just watched one video beforehand, I may have done my proofs differently. And I think one thing I learned is in future, instead of just trying to do something, like when I'm writing a program, for example, I'm so used to just trying it, watching it not work, and then try solve why it's not working. Instead of reading documentation, for example, and figuring out exactly what different things do, and then structuring a program around that, instead of just trying something, giving it a go, and then trying to fix problems, if that makes sense. But yeah, I think that's kind of what I've learnt, and what the main thing that I think I can apply to myself to take away from this module.
That's amazing.
I think for me, this whole module was extremely interesting. This final project was a massive.
Just excuse me, I'm just quickly gonna get my charger. I'll be right back.
The final project was a massive. How do you say it? Like a challenge, a massive challenge for me, especially since I fell behind very easily. Since I budget like 2 hours a week for math, and then suddenly it became 5 hours. Just material, and then trying to figure out something other than that, and then us starting with graph theory and me not knowing coding at all and being overwhelmed by the thought of Sophia. Yo, that was very scary for me. So in general, this final project was very, very challenging. And due to that, like kind of stress, it took very long for me to actually get into it. But other than that, this module has completely broadened my perspective on math. Especially like I keep thinking about it, but I joined the module very late. It was literally just before we started getting like a lot of random mathematical, like random sentences, and we had to put it into mathematical structure. Like that Peter likes a friend of Jane, and Jane likes a blah blah blah. That was mind blowing for me. That was so cool. I enjoyed it so much.
You can actually prove something like that.
Yeah, and then for my final assignment, I made like the randomest things. Like there is a drumstick in a chicken. The chicken is in the pot, which means the drumstick is in the pot, and stuff like that. And it just like completely changed everything for me. Like how, if you in real life, if someone says, "But that implies that," and then I'm like, what is your steps of implication? It's fun.
Well, if
It
is false, then you can prove anything.
Yeah.
Which is
It just it made math. It made me think of math in a way that I've never thought of it before, which also like weirdly helped with like my classes as well with my kids. Just to think about math a little bit deeper, think about it completely differently. So I didn't necessarily get like a big revelation from this project in particular, but from the module in general, but like the most profound for me was the first seminar, and then everything built on that. So yeah, I thoroughly enjoyed this module.
I think for me, I think this semester, the project was it was sort of a big dark cloud looming over our head, kind of. I think from the first seminar, obviously I didn't come out of that one too well. That last project also didn't go quite as I thought it would, and obviously I'm not that great at proofs and bracket notation, but sort of going back to what Matt was saying about trying and failing and trying and failing, I think overall it's just part of life. They say that experience, if you have experience, it just means you've failed more than other people have tried. So I think that's quite a valid statement.
That's a good statement.
But I think I mean maths it's very complex, and there are lots of interesting topics that stem from it and ideas. It's really, it is quite an interesting thing, and sets especially, just because sort of sets, it's like the building blocks. It's something that you just have to agree on, the very base elements that you have to understand and come to an agreement with other people, sort of, you know, the very, very basic thing, like what is an element of a set. You know, it's not really something that you can, or that I feel that you can kind of prove, like what's an element is. Like, you know, there's sort of the basic definitions that are just there, and it's kind of like, I suppose, trying to understand the universe. You know, there's all sorts of things, and there's things that we haven't discovered yet, and that we don't understand yet. For some of them, you know, for some of us, it might be how to prove things in bracket notation. But I think it was an interesting project, and I mean, I looked at some very interesting things, completely sort of off topic, but yeah, it was an interesting learning experience. And yeah, I mean, there's all sorts of really interesting things in math that like haven't been solved yet. And you know, when I sort of thought of this project right at the beginning, I was like, oh yeah, we could think of one of these things that we can't solve. And, you know, you sort of, it's quite tempting to go off on a tangent that really has nothing to do with sets or anything like that. You know, there's so many interesting things, but yeah. Overall, I think it was good to sort of get to meet everyone. It was also pretty cool sort of learning that we kind of, you know, this is a really small world. Like Razan goes to my church.
Yeah, I mean, I discovered it like after some of our team's meetings. I first actually saw it when we sent our schedules through on the WhatsApp group. I was like, oh, Gareth has Bible study there, and then there's one of his at the same church, but let's just see.
Yeah, and then I'm also Matt STEMI for computer science. It's like
we also I actually went to primary school together.
Yeah.
And I first didn't realize it when I saw, like, you know, the teams, like you only see the initials, and at first it didn't like occur to me that it's the same Joseph. And so when we met him first, I was like, how did I miss this? I was like, Joseph, oh my God, it's you. Yeah, sorry, Joseph. Just what did you learn out of this whole project?
I think, well, the module for me taught me, it made me think a lot different about math. Like, say, if we calculate something and we get to an answer, I usually didn't care as to whether that was the correct answer, but this module made me question that a bit as to why that is correct. So now I think differently, as opposed to just, say, following a kind of algorithm, just a method to calculate something. And I think the project for me, mostly it sort of solidified or helped me a lot with these bracket proofs. And just also how effective teamwork can be. I think you guys have been a really nice group, so just thank you for that.
I think maybe to add on to that, the teamwork, in all the meetings, in all the discussions, it was kind of said, yeah, your structure, you have to have like at least 20 proofs or something in your paper. And then I'm not gonna lie, I was sitting there like, how are we gonna get a document that is this long? But we ended up having a document of 55 pages, and I was very impressed and amazed at just working together how much we can get done. And you guys worked hard, and yeah, well done on the year, I guess.
Yeah. I'd also actually like to add on to Joseph's comment on like that this module kind of taught you to think on why something is correct, not just to accept that it's correct. I actually think from the first lecture we had, something like switched in me. I was like, so excited because this is like type of questions that I had about mathematics that's being answered now that I had throughout my school years. Like if we were taught something, I would question, but like, how do we know that is true? Like, how do we know that, I don't know, plus even exists? Or, you know, like, yes, you can kind of deduce it from reality, but there's certain things like, and properties from multiplication and plus, like commutativity and stuff, that I was like, but how do we know this? How do we get this? Like, normally in science, we do experiments and we get to conclusion, and you're like, okay, well, that's what we see is the truth. But with maths, it seems like it's almost invented in a sense. And if you look at the history of maths, like it is in a sense, but it comes down to that question of is math invented or discovered?
Yeah.
Is it, what do you call it? Is it
discovered? Was it invented or was discovered?
And in a sense, I think the answer is both, because like to get to the mathematical system we have now, we have to define things. And I think that's something I really learned also, like even just in everyday life. You can't actually have a discussion about something if you don't really know what exactly you're talking about. And that's what this module taught me, is like being precise about what you want to talk about, because in a sense, a theory is like a discussion on something and you have to know exactly what you're talking about. So a lot of arguments in real life comes out of us not really being precise enough with what we mean, and then ambiguity playing a role. Like it's so important to define something before you use it and all be on the same page. And that's what I find fascinating. But it's really cool to see that you can actually prove that the things we know to be true is true. But I definitely went on it. I also just got distracted many times when I started reading up on the history of mathematics and how set theory is like the unifying theory. That, I mean, it actually only in the 1900s that they actually found it to be the central theory that combines everything. What are you laughing at? My dad. What did you do?
I just picked up my jersey.
Oh, okay. That's my dad. The Zen master. It was just, I think I'm talking too much now, but it's really like interesting reading up in the history of mathematics and like following the lives of the mathematicians that invent these, discover these theorems. I often get distracted in my mathematics textbook by reading the like history blocks instead of the actual work.
Talking about something we always just assumed is true in mathematics, this year I started thinking, like, why is a minus times a minus a plus?
Oh, I thought about that a lot.
I'm like, because we were all just taught, just take it as is.
Yeah.
Just take it, a minus times a minus is a plus times a minus is a minus.
And it's like, probably because someone can prove it to have that property. And I wish actually that's like a simplified version of this module was taught at school, or maybe like a course in logic or philosophy, because it's very important to know where something comes from. And I really struggle just accepting things, like even in like genetics or biochemistry, like university kind of in some subjects it teaches you to just accept facts. And I feel like science is something that you have to question. And I felt like questioning helped me in this module. Like instead of going, like I think my what do you call it, a tendency to go back to the basics and really understanding the basics before moving on helped me in this module. Whereas in other modules, it's my downfall, because I spend too much time in wanting to, let's say in the other normal mathematics module, I spent too much time trying to understand a theorem instead of just practicing the application of it. I think this is what this module taught me, is that, okay, there really is, you can actually trust what other mathematicians come up with.
I think the downfall of questioning things is you run out of time. I think that was my downfall this seminar. It's like I completely ran out of time.
But at the same time, it's necessary. But overthinking can also be.
Saw a pretty interesting video. A little bit off topic, yeah. But it's I think it's the 3x plus 1 problem.
Oh yes, the unprovable.
That's the one guy speaking about it was like when he first discovered the problem, people just said, "No, don't waste your time," and then like 40 years later, he's like, "Yep, I've wasted my time."
But I mean, that's happened before. Like in the past, there's some mathematicians who warn other mathematicians never to go into the topic of never what do you call it? Deal with the topic of infinity, because you will never get out of it. And then some of your, like, I think it's George Cantor who actually like did thought experiments on infinity, and he actually ended up losing his mind.
Which makes sense.
I'm actually reading this comic book. It's called Logicomics. It's about Russell's life. It's very fascinating, and they kind of explore the idea of how logic and madness go hand in hand, and like focusing so much on logic can make you mad in a sense, but also madness could lead you to logic, which I don't quite agree with. But it's an interesting theme.
Yeah.
Well, there's an interesting proof. How do you prove, okay, let's say you're in a mental asylum. How do you prove you're not crazy? It's a scary one, because like anything you say, people won't believe you, because they're like, "Nah, you're crazy."
Just don't.
Yeah, I think that's like one of my biggest fears is actually ending up in a, because of movies. It's like if you're there, you can't get out. So that's one of my biggest fears, I think.
Yeah.
I think a good movie that represented that was Shutter Island. I don't know if anyone had seen that.
yeah.
That
I
was
think possibly, yeah.
If you haven't, it's a good watch. If you ever like not sure what movie to watch, you should watch Shutter Island.
I must say, I don't know about you guys, but if you start dwelling on things and you work with your own, like, if you fool yourself in like this module and you work with your own mistakes and you go off in tangents, you kind of do feel like you're losing your mind. Like you're entering this underworld and you need someone to like rescue you from it.
Yeah. It was funny. I was looking at so that sort of idea that's at the bottom of our document with the numbers represented as sets, and I was sort of looking at how you sort of denote coordinates or sort of ordered pairs, and like if you look at the number 2, which is made of 0 and 1, it looks like an ordered pair. So it's like, it got me thinking like, what if like the numbers in set notation is like coordinates, but each number is represented by another dimension kind of thing. So like 2 is 2-dimensional, and then 3 is 3-dimensional, and then 4 is 4-dimensional. And like by the time you get to 99, it's like 99 different dimensions. And you're like, wow.
Yeah.
I mean, it's a crazy idea, but I don't know if that's really valid or worth anything.
That's cool doing these thought experiments.
See, this is what I was thinking about when we were supposed to be doing proof.
Yeah, and I was trying to come up with a contradiction with equality. Oh man, it was fun. It was fun going on those like little journeys. Ooh, one thing I want to share about one of the most interesting topics I came across was like throughout the history, like following the history of Russell paradox. Let me just call him Russell. Russell's life is the fact like he wanted to find like a foundation of mathematics, and he wanted to use logic as a basis for doing so. And he wrote this book, and he ended up thinking it was a failure. And he ended up like re-examining his proposition with his assumptions, and then he ended up publishing it anyway. And until the end of his life, he still thought it was a failure. But then, like, I think it was Gödel, what's his full name? Kurt Gödel actually read his book, and I think that book inspired Kurt Gödel to come to the theory of incompleteness, which fascinates me. If you guys want to go read up on Kurt Gödel, I definitely recommend it. So, because he kind of goes into the idea or like the thought experiment of like, how do you actually know whether an axiom is going to lead to a consistent like theory or not, and can you actually prove axioms? And yeah, I think if I understood it correctly. But anyways, I've really
Remember,
enjoyed
what
it.
is the
A bit
time?
off topic.
I was
Yo, it's
sorry
already
about
10
that.
to 11. So
Yeah.
wild. Time flew during
Yeah.
this session, and I think that's kind of a sign. I was kind of enjoying our discussion, and yeah, I hope everyone else did as well.
Yeah. I really enjoyed working with you guys. It was fun to have switched groups and got a new guys. It was nice.
It was nice having people actually wanting to engage.
Yeah.
I think
And we all always engaged, which was nice.
I think our willingness to meet, even especially like tonight, for example, at 9 o'clock in the evening, ready to make our video. But I think 3 of us writing tomorrow. So like I think just our willingness to meet at different hours, not the usual. Oh, cool, we'll meet in the day. It's kind of different hours, and it is separate from when you would be doing other things, and often maybe after we've just eaten supper and kind of showered and that, and then would meet, and then after that maybe work a little bit and go to bed. Which I really enjoyed. I think it added a little bit more like structure to like my own life.
And also knowing that you're not alone is nice. Like, you know, we all struggled to find a starting point with this project. It was quite challenging, but it was good to know we're all in it together.
Yeah.
On that note, thank you for being accommodating regarding meeting late at night.
Yeah, it's a pleasure.
It's like that's definitely my fault.
Sure, Margie, you had it on another level, I must say. Well done. For pushing through, like, what's it, 8 till 7 every day?
Yeah, 8 to 8, but tomorrow again, so
But like every single day of the week, so not even Sundays off.
Yeah.
Oh,
Well
that's
done.
wild. So I think I'm gonna stop the recording here.
Okay.
Cool.
Okay.